In this video, let us take a detailed look into big O, omega and theta notations. Let us start with big O notation. Big O notation is a mathematical notation that is used to describe the upper bound of an algorithm's time complexity. Big O notation describes the worst case scenario of an algorithm. Let us see what do we mean by upper bound time complexity. Consider this graph. On the x-axis we have n, that is a number of inputs, and on y-axis we have time. We know that when an algorithm is running, it will take a certain amount of time. We have already discussed that analysis of an algorithm means trying to find out how the algorithm behaves in terms of time with respect to a given input. In this graph, we can see that as the number of input increases, time also increases. When we look into big O, we are representing an upper bound or the upper time limit. That is the maximum time for a particular number of input or the worst case. So we need to represent this as a mathematical function. Let us see the definition of the mathematical function as given here. The function f of n is big O of g of n if and only if there exist positive constants c and n naught such that f of n is less than or equal to c into g of n for all n where n is greater than or equal to n naught and c and n naught are constants c greater than 0 and n naught greater than or equal to 1. This definition says that the function f of n is equal to big O of g of n, where g of n can be considered as upper bound if and only if f of n is less than or equal to c into g of n. C is a constant value, and when you multiply it with g of n, it should be equal or greater than the function f of n. Where n is greater than n naught, that is, after a particular value of n, this condition holds true. N naught greater than 1, that is, input has to be greater than 1. N naught N naught will denote that point beyond which c into g of n is above the function. To understand this better, let us take an example. F of n equal to 2n plus 3. Now, in order to represent this in terms of big O notation, we have to find a g of n, and a constant c into g of n should be greater than f of n. Now let us assume g of n to be n. Substituting it in the mathematical function we have learned, 2n plus 3 will be less than or equal to c into n. Let us assume the value of c is 5 and n is 1. Substituting this value in the above equation, we will get 2 into 1 plus 3 is less than or equal to 5 into 1. That is 5 less than or equal to 5. The condition holds true here. Hence, we can say that g of n can be n and f of n can be represented as big O of n. Let us take another example for c and 2. Let us substitute the value c equal to 4 and n equal to 2 in the same function. So it becomes 2 into 2 plus 3 less than or equal to 4 into 2. 7 less than or equal to 8. Condition holds good. So we can conclude that f of n can be represented as big O of n. Here are few more examples. A function 3n plus 2 can be less than or equal to 4n for all n greater than or equal to 2, hence can be represented as big O of n. Similarly, 100n plus 6 less than or equal to 101n for all n greater than or equal to 6, hence can be represented as big O of n. 10n square plus 4n plus 2 can be summarized as less than or equal to 11n square for all n greater than or equal to 5, hence can be represented as big O of n square. A function 1000n square plus 100n minus 6 can be written as less than or equal to 1001n square for all n greater than or equal to 100, hence can be represented as order of n square. Now, if we look into the previous example, whatever we have checked here, f of n equal to 2n plus 3, we said g of n can be considered as n, so that this 2n plus 3 is less than or equal to 5 into n, and also 2n plus 3 is less than or equal to 4 into n for n greater than or equal to 2. Now, this condition also holds good for g of n is n cube or g of n as n square, that is 2n plus 3 less than or will be less than or equal to c into g of n square, or 2n plus 3 will be less than or equal to c into g of n cube for any value of c, like the minimum value of c as 1. It will hold true. But one thing to be noted here, we should always use the closest function because there is no use of writing higher order functions. Now let us look into omega notation. Omega notation describes the best case scenario of an algorithm. It represents the lower bound running time complexity of an algorithm. It tells what is the fastest time your algorithm can run given an input time. Let us see how it can be represented mathematically. We can say that the function f of n is omega of g of n if and only if there exist positive constants c and n naught such that f of n is greater than or equal to c into g of n for all n where n is greater than or equal to n naught, and the constant c should be greater than 0 and n naught should be greater than or equal to 1. Let us understand this with the help of an example. Let us take the same example as the previous. Let f of n be 2n plus 3. We have to write f of n such that f of n becomes greater than or equal to c into g of n. Let g of n be n. Substituting the values, we get 2n plus 3 greater than or equal to c of n. Let us assume the value of c is 1 and n is 1. So it becomes 2 into 1 plus 3 greater than or equal to 1 into 1, 5 greater than or equal to 1. Holds good for the condition. Similarly, let c be 1 and n be 2. Substituting, we get 2 into 2 plus 3 greater than or equal to 1 into 2, 7 greater than or equal to 2. Again, it holds good for the condition given for omega. Hence, we can say that f of n, the given function f of n, that is 2n plus 3, can be represented as omega of n. Here are few more examples. 3n plus 2 can be represented as 3n plus 2 greater than or equal to 3n for all n greater than or equal to 1. Hence, it can be represented as omega of n. 100n plus 6 greater than or equal to 100n for all n greater than or equal to 1, hence can be represented as omega of n. Let us take another example, f of n as 10n square plus 4n plus 2, which can be written as greater than or equal to n square for all n greater than or equal to 1, hence can be represented as omega of n square. So omega of n square or omega of n and omega of n in this example is the lower limit of the functions given here. Now let us learn about the theta notation. This specifically describes the average case scenario of an algorithm. It gives the most realistic time complexity of the algorithm. Mathematically, we can represent theta notation as the function f of n is theta of g of n if and only if there exist positive constants c1, c2 and n naught such that c1 into g of n less than or equal to f of n less than or equal to c2 into g of n for all n greater than or equal to n naught, and the constant c greater than 0 and n naught should be greater than or equal to 1. Let us understand theta notation with the help of an example. Let us consider the previous example we have taken, that is f of n equal to 2n plus 3. So according to the mathematical equations, f of n should lie between c1 into g of n and c2 into g of n. That is c1 in f of n should be greater than or equal to c1 into g of n and less than or equal to c2 into g of n. Based on the previous example, let us consider g of n equal to n. Substituting, we get c1 into n less than or equal to 2n plus 3, which is less than or equal to c2 into n. Let us take value of c1 as 1 and c2 as 5 and let n be equal to 1. So we get 1 into 1 less than or equal to 2 into 1 plus 3 less than or equal to 5 into 1. So 1 less than or equal to 5 less than or equal to 5. Condition holds good. Hence, we can say that the function f of n equal to 2n plus 3 can be represented as theta of n. Let us take another example with varying values of c1 and c2. Let us consider c1 as 1, c2 as 5 and n as 2. Substituting, we get 1 into 2 less than or equal to 2 into 2 plus 3 less than or equal to 5 into 2. That is 2 less than or equal to 7 less than or equal to 10. Condition holds good again here. Hence, we can conclude that f of n can be represented as theta of n. So, in theta of n, you can see that we are bounding the upper and lower limit. With this, we have identified the methods to represent a function f of n as order of n, omega of n and theta of n. That's all for today. Thank you.